Good day, everybody. Today I want to look at something called Jensen's inequality, and that's going to give us an indication of what to expect if we have a convex function like e to the x, and if we exponentiate a function first and then integrate it, versus if we integrate the function first and then exponentiate that result. Now, there's some requirements going on. I've got two versions here. The second version is the one I prove. It could easily be modified to the first one. Just a quick look at the second version. I've got h convex on 0 to infinity, all positive reals, and f is non-negative, so each output of f is in the interval where h is convex. Then we've got also have this non-negative function p that has to be integrable and non-negative, and its integral is also positive, so I can divide by it. And then I need this also in the interval where h is convex, which of course if f is non-negative and p is non-negative, this will be in the interval where h is convex. That was the only change. This first version, I just say h is convex on an interval I, and each output of f is in that interval I, and the integral, this fraction, has to be in that interval I where h is convex. So that's the only difference between these two. Just to see the theorem in action, and then also we will look at what's so special about this p. But first I will set p equal to 1 to make things a little easier. So we're just going to kind of do a regular integral on the top, but also to have this denominator equal to 1, I'll have p1, and I'll have the length of the interval also 1. So now the denominator will be 1 in these early examples. So I pick a function. I just picked sine, and sine is positive on the interval from 0 to 1. And what my convex function, though, is going to be e to the x. So I'm going to exponentiate sine and then integrate it and compare it to integrating sine and then exponentiating. And so if I integrate sine and then put that value into my convex function e to the x, after I integrate, I get this result. But if I compose sine with my convex function e to the x before I integrate, I get this value, and this value is bigger. Notice the length of the interval is 1. And again, that's the result of the theorem. If you compose into h first, it's going to be bigger than if you do the integral first and then compose into h. A couple more examples. E to the negative x is also concave up or convex. So if I integrate sine, get the same result, and then substitute that into e to the negative x, we'll get this result. Or if I compose sine into e to the negative x, we get this. And then if I integrate, so if I do it before I integrate, I'm getting a bigger result than if I do it after. And one more convex function for the interval 0 to 1. How about x squared? So x squared is convex, concave up. So I've kept f sine the whole time, but it doesn't matter, as we'll see by the theorem. So let's see, integrate sine, same result, then square it and compare that to squaring sine first and then integrating. That's a bigger result. But again, we don't have to just deal with positive. So if I look at sine on the interval from -2 to -1, sine is now negative. And again, it doesn't matter what f is doing, only the convex function. So I'm going to compose this into arctangent. I mean, I could pose into e again, but I want to do arctan. Now arctan is concave up on the interval from negative infinity to 0. So if f's outputs are negative, then we're in the interval where arctan is concave up. And so if I integrate sine, again the length of the interval is 1, I get this. And then if I put that result into my convex function arctan, after I integrate, I get this. Or if I compose sine into arctan before I integrate, I get this. And then doing it before you integrate is bigger. It's actually smaller in magnitude, but since they're negative, this number is greater than that number. So that was an example of here where I'm not going to worry about being positive. Also, the inequality is reversed if h is concave on the interval. Like for example, arctangent is concave down on 0 to infinity. So here I'll look at sine again, but from 2 to 3 sine is positive. So if I put it into arctan, I'm subbing it or composing it into a concave down function. So integrate sine, length of the interval is 1, compose it into arctan, I get this result. If I do arctan of sine before I integrate, and then integrate, well, now this result's smaller. So the inequality got reversed. And one more concave down function. So arctan is concave down. So is natural log. That's concave down. 0 to infinity. And these are integrable. So if I integrate sine 0 to 1, and then natural log of that number, I get this. Or if I compose sine into log and then integrate, I get this number. And again, now doing it before is a smaller number than doing it after, putting it into the concave function. So if you're concave down, doing it after you integrate is a bigger number. And I guess before I do the proof, I will also look at this P. And actually it was quite handy in what I wanted the inequality for. Because I was considering an application where I was finding the average slope of tangent lines on an interval. And that's easy to do with respect to x. The average value of a function, this is just an arbitrary function, the average value of a function with respect to x, you can just integrate that function and divide by the length of the interval. Here I kind of do it as a line integral because I kind of want to view these others as line integrals. So you integrate the function, divide by the length of the interval, and that's the average value of a function g. If I want the average value of a function along a curve with respect to arc length, then I essentially want this line integral and divide by its length to get the average value. So this is kind of a line integral with respect to arc length. So that would give me the average value of g if you kind of take points equally spaced along the curve itself, y equals f of x. If you take points equally spaced on the x-axis, you get this average value. The more points you take, the closer you converge to this value. And I also considered if you take points equally spaced vertically, kind of along the y-axis, so that would be the average value of g. Again, it's another line integral. dy is f prime dx, and ds is this. So if we look at these three things, notice it's a lot like Jensen's inequality, where I have the p integral of p dx and then g times p. So here the p is 1, here the p is this quantity, and here the p is f prime. So it's kind of convenient that for average value, the form of Jensen's inequality is perfectly made. And so what I was comparing, though, was not average slope, but the average angle. So this would be the formulas for the average slope if you replace g with f prime. But I actually wanted to, after I did that, I wanted the average angle. So I replaced g with arctan of f prime and found the average angle and compared that to arctan of the average. So the angle the average slope made. Okay, so, and then from Jensen's inequality, if you put the arctan of f prime in here, well, more in for g, so arctan of f prime goes in for g in each spot, then the average angle is always going to be smaller than if you do the angle of the average slope. So that's what came out. And again, it was Jensen's inequality with p equal to 1, and then this and this. So Jensen's was perfectly made for what I wanted it to do there. So let's look at the proof. So again, I'm going to look at the proof of this version here. It could easily be switched to where you just have an arbitrary interval of convexity, and then as long as f outputs into that interval and this integral is also in that interval where h is convex, it would work. But all right, so the way the proof goes is that you set x naught equal to this fraction, integral of f times p divided by integral of p. And since p and f are non-negative, this will be greater than or equal to 0. And since h is convex, you can look up or verify that a convex function is always above its tangent line. So h will be above the tangent line at x naught for all x greater than or equal to 0. So what that means is, so here's the equation of the tangent line. It's the slope times x minus x naught plus the value. So that's the equation of the tangent line for h at x naught. And then h of x has to be bigger than or equal to that. Now this is true for all x. So, well, let's see, first I distribute one tiny step there. But if it's true for all x, then in particular, I can replace x with f of x. So there we go. Evaluate at that point in the interval. Right? So this is the only variable. It's true at x, it'll be true at f of x. Since p is non-negative and has a positive integral, we can multiply both sides by p and then integrate, and that will maintain the inequality. So multiply both sides by p, integrate, and then divide by the integral of p. Again, so I'm not dividing by 0, and it's a positive quantity. So I now have this integral, and I'll distribute this p into, so now I have 3 integrals. And there's a lot of constants here, so if you factor these constants out, the h of x naught and the x naught h prime of x naught, we now have these integrals, and now divide p into all 3 terms. Of course, here they're gonna, the integral of p's will cancel, so you just get these 2 quantities. And then over here, I get h prime, that got factored out, and then integral of f p dx over integral p. But this was just how I defined x naught, so I'll replace this with x naught, and now actually these 2 terms cancel, so I just have h of x naught is less than or equal to this. But now I'll remind us again, what was x naught? X naught was this fraction, and so that proves the inequality for convex functions. And that's what we wanted to show. If h is concave, that means negative h is convex. So if h is concave, then the theorem would be true for negative h, and then multiplying both sides by -1 gives the result for concave down functions, concave functions. The inequality gets reversed. If we look up Jensen's inequality, often there's a finite sum version, which actually follows from what I'm about to show, but I'm not going to mention it. But usually it's mentioned in the context of a probability measure space. And that just means the measure of your space is 1. So if you have a probability measure space, and if f is a positive mu integrable function and h is convex on 0 to infinity, then h of the integral is less than or equal to the integral of h composed with f. And sometimes they bring this up in terms of moments. So x or f is always like x, and then you could square or whatever, and those will be concave up. So you can see that squaring first and then integrating is going to be more than if you integrate first and then square. So you'll see like e of x and e of x squared. Well, actually, you'll see e of x squared is greater than e of x quantity squared, and so on. The inequality is reversed if h is concave down. I did do the proof. Now it's identical, except here, since the measure of the whole space is 1, we don't have that p or divide by p. But I'll show how this implies the p after the proof is done. Anyway, the proof is really the same. So first, set x naught to be that integral. Here it's just this simple integral. There's no p. And so note x naught is greater than or equal to 0 because f was not negative. Again, we could generalize that if you have h convex on different intervals, but let's stick with 0 to infinity. So there's the tangent line distributing, and I can replace x with f of x. It's all the same steps for the most part. There's no p to multiply, so now I just integrate both sides and then integral the sums, the sum of the integrals, and I factor out the constants, and now I've got these 1s, and now the integral of 1 is just going to be the measure of omega, but the measure of omega is 1 by hypothesis. So we've got h prime times this integral, but what was this integral? X naught. These two cancel, which simplifies to this, but then what was x naught again? Now I'll sub it in, and there's our result for convex functions. And again, if h is concave down, that means negative h is convex. So there we go. So that's the way it's usually seen. And then actually the version I proved, I mean, it was like kind of identical proof, but it's a special case of what was done. So that's why it's usually you wouldn't see it in this form. But if p is a positive mu integrable function and f times p is positive as well, then h is convex, and if h is convex on 0 to infinity, then we have what I first proved. And the proof would just be if omega is that interval AB, set the measure of any subset of AB to be the integral over A of p dx divided by the integral over omega is AB, p of x. So in other words, if you know your measure theory, this is just a way to make another measure, right? So if you have one measure, like Lebesgue measure, then you have other measures just by integrating a positive function gives another measure. and then this normalizes it. So if I do the measure of the whole space, AB, it'll be 1. And then in the other subset, it'll be some fraction. So we can then use the previous theorem using this measure. So that gives this result. So this is actually a corollary to the theorem. So that was how I needed the inequality, and so I modified the usual statement to the form I needed, even though technically this is just a special case of the usual form, which gives us the way I usually do it. Alright, so anyway, hope you enjoyed that, and thank you for watching, and keep doing math and enjoy the rest of your day.